Testing, 1, 2. Speak. All right, we're good? All right, let's see if we got this one? No, a little bit. Let's crank it up a little bit. All right, we good, John?
It's a sound band.
All right, now we good?
Oh, it's probably using this microphone.
Yeah, that's the issue we were having.
Hey, you tuned into the stream? Tune into the stream and tell me how the audio is. Stream.rtsec.club. Talk, Owen.
Yeah. I think it's just a Twitch one. I think it's just a Twitch one. Really? Interesting.
Hey, have the mic.
Testing, 1, 2, 3. Speak. John, come on, we're killing us here. We're 7 minutes behind. What time do you have to take off? You good? Okay, sounds good.
Yeah, the stream's good.
We're good?
On Twitch, yeah.
Audio? Like you can hear me speaking?
Oh. It sounds like you're talking through a mic from like the 70s.
Yeah, I did put it right at my mouth. There's no way it was coming through that.
The audio's fine. All right.
Audio's fine? Ready to kick it off?
We're kicking off.
Yeah, it sounds like you're talking from the 70s.
Ah, perfect. That's what I love to hear. All right. Thank you, everybody. Can we get a little bit of quiet, please? Hush. Does this mic work? There we go. All right, thank you, everybody, for coming to week 5 of RITSec. There we go. If you have not already, please head over to signin.ritsec.club so we can record that you were here so you get all the cool member benefits later on in the semester. While we're doing that, we'd like to give a little shout out to our sponsors. We love them very much. Without them, we couldn't do all the fun things we do. Yeah. Let's give a little clap. Give a little clap for our sponsors. Yeah, we got a new one on the list this week, Expel. I think we're going to be hearing from them later, so that should be a pretty cool talk. I'm excited for that. If you're not following us on social media, you should do that so you get all of our cool updates and stuff about who's doing what, when stuff's happening, and all the neat things that happens around here. All right, some quick announcements. We now have a public GitLab server, so if you want to host some code on our servers, feel free to sign up at gitlab.ritsec.cloud. It's pretty cool. Shout out to our ops team for getting that up.
We will soon have a continuous integration server.
Oh, we're soon going to have continuous integration? Look at that. Way to go, guys. Keep it up.
Now we are.
Oh, we already have continuous? Even better. Other than that, all right, so if you're interested in being the Junior Tech League, if you think the challenges we make are pretty cool and it's something you want to help with, send your resume on over to junior-techlead.ritsec.club. Troy was the Junior Tech Lead last year, and look at him now. He's making awesome challenges for you every week. So if that's something you find interesting and something you might want to do for the next couple weeks, into next year, hopefully, if you do pretty well, like Joy does, please sign up. I help him with challenges, other people have helped him with challenges. It's pretty fun, and you get to help other people learn. So it's a cool thing. Our average, normal disclaimer, everything we do here is educational. We don't want you to do anything malicious with the stuff we teach you. Be good. And without further ado, we have a special guest speaker for us today. Professor Weissman is here to teach us a little bit about networking. I've heard this talk a couple times, and it is one of the best ones of the semester, so give it up for him. There we go, guys. Put this one on too. This is for our stream.
Okay. So let's see.
Let's get on straight.
Wow. Bear with me. It's flickering. I have a dongle to go USB-C. Give me a second there. There we go. All right, how's everybody doing today? Awesome. If you haven't had me yet for a class, I look forward to having you. If you've had me, you might have seen some of the shtick I'm about to do today. So if you might know what's coming up, don't let on that you know what's coming up. And if you know what I'm talking about, you know what I'm talking about. That's all I'm going to say for now. I want to begin by telling you a couple of funny stories that happened to me over the recently completed summer. I thought you might get a kick out of a couple of these stories. My wife and I and our two kids, we live in a beautiful home in Brighton, not too far from here, about 20 minutes from here. And over the summer, a bunch of families moved into the neighborhood. And we happened to like some of the families, we happened to hate some of the families. So we wanted to become friendly with the families that had kids around our kids' ages, around 7 and 5. So we befriended a few families, and my wife made a care package for one of the families, and she said, Jonathan, go ahead and deliver this package to the Smiths. Now, I knew that a bunch of houses in our neighborhood recently had a turnover. I wasn't quite sure which one the Smiths actually moved into. So this was on a Sunday night. It was late July. I needed to get that care package to the Smiths, so I wasn't quite sure what to do. I knew that the family name was Smith. I didn't know what house they actually moved into. So what I did was, I'm also a musician. I have a 500-watt amplifier. I brought that outside. I hooked up a microphone, and I shouted, even though I didn't really need a shout with a 500-watt amplifier. I shouted on top of my lungs, "Hey, Bob Smith, which house do you guys live in?" And this was 11:30, around 11:45 at night, and I woke up the whole neighborhood. In fact, I woke up my own kids. My wife was so pissed off. She worked so hard to get them to sleep. I'm the fun guy. She's more of the stickler for details. I said, they could play. But you know what? Besides waking up the whole neighborhood and having people throw things at me and cursing me out, "Oh, you stupid Weissman, shut up." What happened was, I did happen to get Bob Smith's attention. And what he did was he very discreetly walked over to my house and said, "It's actually 123 Main Street, and try not to be so annoying in the future," and walked back home. Later that night, after we put the final touches on the care package, I took it and I walked directly to the Smith's house after getting the address from Bob, who walked over to me, and I delivered the package. That's story number one. It's pretty cool. Pretty exciting, no? Summer activity. Second exciting summer activity was, I'm originally from Staten Island, New York. My parents still live there. So my wife's family is originally from Philadelphia, Pennsylvania, and they still are in the area. By the side note, you know the difference between in-laws and outlaws? Outlaws are wanted. They're a tough crowd. I like them though. So what happened was we took some trips to my in-laws. We took some trips down to my family in Staten Island. And what happened was we got back to Rochester after one of those trips, and we were unpacking, and then it's like a heavy bag. It was Noah's bag. Kids are Noah and Jacob, and Noah's bag was a little bit heavier than I quite remembered it when I was unloading the car. And I looked in there, and I found these two big, heavy candlesticks in there, and I said, "Noah, where'd you get these from?" He goes, "Grandma, my mother." And I'm like, "She gave you those?" And he goes, "No, I took them." "Cool, they're pretty shiny." So I said, "Wait a minute. You took the candlesticks?" And he goes, "Yeah, I took the candlesticks." I checked my email and had like 500 emails from my mom. "Do you see my candlestick? You see my candlesticks?" And I wrote back, "Actually, we got them." So I wasn't about to drive 350 miles down to New York City again, Staten Island, New York, and drive the candlesticks back. So the logical thing that I did the next day was I Googled for the nearest UPS store where I live in Brighton. It came out to be a UPS store on Elmwood Avenue. And I brought the candlesticks in a brown box. I put it in the brown box, and I gave it to the UPS folks, and they took care of the rest. So that's another funny, cool little story that happened over the summer. Nothing to do with networking, but just pretty funny. Would you agree that it's pretty funny? Pretty funny. Thank you, thank you. Local versus remote communication as far as networking goes. The very first thing any device that has traffic to send in the world of networking does is that device has to determine whether traffic is local or remote. Now, in terms of local versus remote, we're talking about devices that are connected via switches to qualify as local. What does that mean? That means they're on the same network, they're on the same LAN, they're in the same broadcast domain, they're in the same subnet. These are all terms that mean the same thing. So from a non-technical perspective, think of somebody in the same area as you, whether it's the same block or the same city or the same state. Some geographical location will determine, yes, I am close, or no, I am pretty far. For traffic that is local, if a device has to send traffic to another device on the network, it only goes through these things called switches, layer 2 switches. And the traffic is actually delivered directly from the source to the destination. There's no need to get any other middle device in the mix. It's direct communication from source to destination if the traffic is local. But on the other hand, if traffic is meant for a different network, whether that network is one hop of a router away, or 10 or 15, it doesn't make a difference, that source cannot send the traffic to the destination directly. The source has to send traffic indirectly through a different type of a device called a router. So if the sender of the traffic says, oh yes, this destination is on the same network as me, the traffic is local, in that case, the traffic is delivered directly. It only goes through these devices called switches. Just move this out of the way. If the traffic is meant for some other network, whether it's one block or one city or one state, whatever the geography is, in my first example, the traffic has to go through this device called a router. So the obvious question is, okay, how does the source determine whether the traffic is meant for a local recipient or a remote recipient? So let's start talking about this thing called an IP address, and we will be focusing exclusively on IPv4 addresses. If you want to see IPv6, see me in my special summer class, and I'll talk more about that at some point. But IP addresses, some ways we describe these IP addresses. We use words like logical and software and hierarchical and geographical, which means it's just like a zip code when you think about it. It's just like a zip code that ties you to a certain portion of the world. And it's hierarchical, which means that there are a couple of parts of the address that indicate different levels of addressing. For instance, if you take a look at this address over here, 172.16.254.1, we got the base 10 version right over here. We got the base 2 binary version right over here. Some of that IP address represents the network identifier, which means everybody on that same network will share the same first amount of bits. The other part of the IP address here represents a host ID, which is a string unique to every device on the network, sort of like a serial number or a registration number for every device on the network. So the hierarchy is the first part of the IP address, the logical address, assigned to you via software, nothing to do with anything hardware, is shared by everybody on the network. And the second part is a unique identifier for each device on the network. And if you take a look, of course, when you have the binary representation, you have 32 ones or zeros, 32 bits. Each grouping is called an octet because that's the prefix for 8. And we say IPv4 addresses are 4 bytes long. So here's now the $25,000 question. How do we know how many of those 32 bits are for the network and shared by every device? And how do we know how many are unique in their entire string to represent certain devices on the network? Just looking at that IP address, there is no way you can tell. You need some other entity known as a subnet mask. A subnet mask is also a 32-bit identifier, but the purpose of the subnet mask is to clearly state which of the 32 bits in the IP address are network bits and which of the 32 bits in the IP address are host bits. And the way it works is you take your IP address and you take the subnet mask. You can't tell what network you're on without knowing what your subnet mask is. And you logically AND, A-N-D, not add, but you logically AND them together. When you take an IP address and you logically AND it with your subnet mask, bam, all of a sudden you're going to see your network identifier. I have a couple of examples. We're going to see how that works in a second. But let's just use a very simple base 10 example. If the subnet mask for this particular IP address is 255.255.0.0, I could look at that IP address and know the first 2 octets are reserved for the network ID, and the last 2 are reserved for the host portion, a serial number for each device on the network. How do I know that? Well, IP addresses only follow one pattern. A string of 1s followed by a string of 0s. If the IP address is lined up with the subnet mask, you've got 2 straight rows of 32 bits. If the subnet mask bit is a 1, that means the corresponding bit in the IP address is a network bit, shared by every device on the network. If the corresponding bit for the IP address and the subnet mask is a 0, that means that the IP address bit is a host bit. So the subnet mask can't follow really any pattern for 8 bits. It's only got to be a pattern starting from the left of 128, 192, 224, 240, 248, 252, 254, 255. We're adding 1 to those place values going from the left to the right. Highest number you can make with 8 bits is 255. Lowest number you can make with 8 bits is 0. So the subnet mask, if I'm telling you that it's going to be 255, 255, 0, 0 for this particular address, that means everybody in this network starts off with those first 2 octets of 172.16, and now the last 2 octets are going to represent host octets. Again, some unique string to identify every device on the network. So far, so good. And then we're going to see the logical AND in a second. But the next question I want to address is, well, how does the source determine whether the destination is local or remote with that given information? So I made a beautiful little color-coded chart for you guys right over here. In story number 1 over here, you got a host with an IP address of 10.0.0.1. And if I'm telling you his subnet mask is 255.0.0.0, that means that this octet for the subnet mask has all 1s, which means all of these 8 bits and the corresponding 8 bits of the IP address are network bits shared by every device on the network. If the subnet mask has 3 octets of 0s, that means that these 3 octets are host octets and are unique in their entire string for each device on this network. Long story short, every device on this guy's network starts off with 10 in the first octet. Those last 3 octets will vary based upon how the addresses are assigned. So 10.0.0.1 wants to send traffic for 10.0.0.2. The absolute first thing that the host ever does before sending traffic is determine whether the traffic is local or remote. Because again, if it's local, the host could deliver the traffic himself. If it's remote, the host needs somebody's help in the form of a router, also known as a default gateway, which is your router interface on your network. We'll talk more about that in a second. So here's what happens. In base 10 up here, the source takes his IP address and his subnet mask and logically ANDs, A and D, the 2 together. Comes up with that 10.0.0.0 IP address, which is not assignable to a device on the network because it means the entire network. The entire 10.0.0 network is represented with the network ID. A good way to check whether you're doing this correctly is every network ID will always have all host bits set to 0. And if you take a look, how many host bits do we have here? We have 24 host bits. They're all set to 0 over here, so that's how we know that that's most definitely the correct network identifier. Here in binary, you can actually see the logical AND process. We bring down a 1 for the network identifier if the subnet mask bit and the IP address bit, that's why it's called AND, are both 1s. Any other pattern pulls down a 0. So if you take a look, if the IP address is 10.0.0.0, the last 3 octets by default are going to turn into 0s because none of the subnet mask bits in the last 24 bit positions from the left have 1. So they come down as is with 0s. But the only ones coming down are the ones in the 2's column over here and the one in the 8th column right over here. 8 plus 2 is 10. That's why the network identifier for the source is 10.0.0.0. So the source says, OK, I'm on the network that I know. It's like you saying, where am I living over here? What's my zip code? You want to do with the telephone? What's my area code to determine a local telephone call versus a remote telephone call? It works the same way. You got to figure out where you are. And that's what the source does. The source figures out where he is by doing the logical AND process with his IP address and his subnet mask. He gets the network identifier. Now the source says, I got to send traffic to this guy, 10.0.0.2. Got to determine whether he's on the same network as me or on a different network. So here's what the source does in that case. The source takes the destination IP address along with the source subnet mask. Now you might say, shouldn't he take the destination subnet mask? Well, number one, subnet masks are never transmitted in any form of networking. You don't know what it is, but you don't even need it. Because if the destination is on the same network as the source, the masks are going to be the same. So the source says, let me take my mask and do that logical AND process with that IP address right over there, Oh, look at this. The two network IDs come out to be the same, so I know it's a local communication example. I know the source is saying right now, I know I could deliver the traffic directly to the destination. I don't need to get no default gateway, and I don't need to get no other device in the mix over here. I could do it all by myself. And if you take a look in the binary, of course, it follows through the same pattern. So that's how the host determines whether the traffic is local or remote. In the next example, I've highlighted the only fields that have changed. In the second example, the source wants to communicate with a destination IP address of 11,002. That's changing from the original 10,002. And the network ID, when you perform that Boolean AND process, I'm adding a 1 in the ones column over here. Instead of 8 plus 2, it's actually 8 plus 2 plus 1 to give me 11. And now this column has two matching 1s in the IP bit and the subnet mask bit. So 1 comes through for the network ID bit. And the source says, wait a minute, I'm on the 10 network. The destination is on the 11 network. That's not local communication. I can't deliver the traffic myself. I got to get it to some other entity known as a router or default gateway at that point. So far, so good? Any questions you want to throw my way before we continue? Let's continue. So first question you might be wondering is, well, how the heck do you get a destination IP address? In my net services class, we spend a good 6-7 weeks digging into everything and anything related to one of the most important protocols in the world of networking, known as DNS. And the DNS overall hierarchical global system will actually blow your mind. Everything that you're going to see with DNS goes on in like the blink of a second, a millisecond. But to make a long story short, because I have about less than an hour left, it takes a name, a fully qualified domain name, and turns it into its corresponding IP address. So anytime you open up a browser and you go to a website, you're not really going to that website address. You're getting DNS to translate that FQDN, that fully qualified domain name, into its corresponding IP address. And that is a global, scalable, hierarchical database that we'll talk about in net services. But that explains how I get the IP address. But now here's an even bigger problem. I have the IP address because of DNS. How do I know which device is in possession of that IP address? When you're here at RIT, if you've ever looked at your IP address on your laptops or on your phones, you'll notice that the IP address here at RIT starts out with 129.21. Last two octets will vary. At home, your IP address will surely not start out with 129.21 because RIT owns that actual Class B block. At home, you'll most likely see 192.168.1 to begin your IP address. That's something to do with private and public addressing and that. And again, that's a story for another day that I don't want to get into right now. But the obvious question is, if IP addresses are software and logical and hierarchical and geographical, how do we know who's got a particular IP address at any point in time? Which device? Is it a phone? Is it a laptop? Is it a desktop? Is it a webcam? What is it? Is it a thermostat? So now we have to go dig a little bit deeper into a different type of address known as a MAC address. The way into and the way out of a device. I don't care what the device is, laptop, desktop, phone, you name it, thermostat. The way that network traffic goes in and out, the physical ones and zeros, the electrical pulses, or if you're into fiber NICs, the light in themselves. But how does the actual traffic go in and out of a device? It's through a NIC, which stands for Network Interface Card. And for decades, I've been saying to industry, stop calling it Network Interface Card because it's been a chip even on laptops and desktops for 20 plus years. It should be called Network Interface Chip, but again, that's a story for another day. We just say Network Interface Card. One of my biggest pet peeves is if you come to me and you talk about the NIC card, and I'll say, oh, do you get your money from your ATM machine? And don't do that double entendre with me. So the point is, a MAC address is actually, look at all these descriptions I've got. They're the complete antithesis of the words I had when we described logical IP addresses. These are physical. These are hardware. There's no hierarchy. It's a flat addressing space, and it's surely not geographical, which means if you go on a website and you buy yourself a NIC, and somebody in California buys a NIC a minute later, you very well could wind up with sequential MAC addresses. We'll talk about how the MAC addresses work in a second. There's no order. There's no hierarchy. There's no reason to think that the MAC addresses are scalable across the world like IP addresses, because they're not. They're like serial numbers. They're like VINs for a car. They're like IDs for a gun. They're like social security numbers. They have no indication other than what the device is at this point. And if you take a look, MAC addresses are 48 bits long, but they are not represented in base 10. They're not even represented in base 2. They're represented in hexadecimal base 16. There are 12 hexadecimal digits in a MAC address, and it isn't even split right down the middle, 50-50. The first 6 hex digits represent what we call the OUI, the Organizationally Unique Identifier, which is a fancy way of saying a special code assigned to a company. Companies like Cisco, of course, have multiple OUIs for all of their devices and all of their router interfaces. Other companies, that are not as big as Cisco, for instance, will still have tons and tons of blocks. You have to register with the IEEE to get your first 3 block double hex character, because remember, how many bits does a single hex character represent? Right, 4. So if you take a look at these 2 hex characters, that represents 1 byte. So take 12, multiply it by 4, you get 48 bits right over here. Point is that these are locked by the IEEE, and they're assigned to manufacturers of NICs. The last 3 bytes that you're taking a look at over here, the last 6 hex characters, that's like the serial number. That's like the host ID portion we talked about IP addresses. The NICs manufacturers will now take those last 6 hex characters and come up with some order for the serial numbers over here. These are burned into the NIC when they are manufactured. So yeah, you do have a nice little label on the NIC that has the actual MAC address, but that's not how the PC gets the MAC address, of course. It's burned into the NIC. That's why we call them physical. That's why we call them hardware. And there's no hierarchy and there's no geography involved with the MAC address. The MAC address is what uniquely identifies an IP address owner at that point. Which device has an IP address? So that's nice and dandy, but now we got another problem. How, if we have the IP address of a destination, how do we find out that destination's corresponding MAC address? How do we send traffic to that actual device and not some generic software logical IP address that could obviously change very, very dramatically, especially on Wi-Fi networks? And if you take a look at my little scoreboard over here, in Wireshark it's going to look a little bit different. I sort of condensed what you'd be seeing in Wireshark. And I'm calling this the scoreboard because we have 4 addresses, not 1, not 2, not 3, but 4 addresses that must be used in any piece of network communication to get from source to destination. You need a source and destination MAC address, and you need a source and destination IP address. So in our first little story over here, let's say host A wants to talk to host B. Host A got host B's IP address. How did host A get host B's IP address? DNS. DNS. I know the name, you give me the number. It's a Beatles song, not one of their well-known songs, but I know the name, you can look up the number. So if you take a look right over here, host A wants to send traffic to host B. So host A has to get host B's MAC address because host A has to send the traffic where the NIC actually accepts the actual traffic coming in. Host A fills out anything he knows. He knows, of course, what his IP address is. In this example, I'm going to call it 10.0.0.1. He knows what host B's IP address is. I'm going to fill that in as 10.0.0.2. This is obviously not a valid MAC address, but let's just say there are 12 A's across the board for host A's MAC address. Question is, what the heck is the destination MAC address? What's that MAC address of host B? So this is where a major networking protocol comes into play known as ARP. It stands for Address Resolution Protocol. And here's what Address Resolution Protocol does for you, the sender of traffic on an IPv4 network. It's 2 parts. It consists of 2 different types of ARP messages. The first is known as an ARP request. The second is known as an ARP reply, which means in an ARP request, host A sends out a network broadcast. A network broadcast is traffic that is not only heard and seen by every device on the network, but it's actually opened up and parsed. And for the most part, almost every device on the network will say, I just wasted my time. That wasn't for me. So the ARP request is going to be a broadcast sent by host A in an effort to fill in this cell right over here so host A could get the traffic over to host B. Host A sends an ARP request. So in our little diagram right over here, host C hears and sees the actual ARP request. Host D sees and hears the actual ARP request. Host B sees and hears the actual ARP request. And embedded inside of the ARP is a message that in Wireshark will give you the human readable form. It says something like, if your IP address is 10.0.0.2, I need your MAC address. So host C says, nope, not me. Host D says, nope, nope, not me. Host B says, aha, you're looking for 10002's MAC address? That's my MAC address. And host B will now send an ARP reply back to host A saying, hey, here's the information you requested. And at that point, the destination MAC address is filled in that network traffic, and now host A is able to send the message to host B. That's not a great system. It's the only way it's done in IPv4. IPv6 actually eliminates broadcasting, but IPv4 is the protocol scheme that absolutely positively requires you to be very disruptive. It's like I gave my students at the end of class I sent an email, or I put something in my courses that said, there's a 500-page PDF waiting for you in my courses. Go ahead and read it. And then on page 499, it says, oh, it's only for Owen. So everybody else would be pissed off. Owen would be like, oh, that's very good. Thank you for giving me that 500-page PDF. I'm sure it was very valuable that I had to read 500 pages. But the point is, it was meant for him. But in the network broadcast, there was no other way to reach him because I didn't know his MAC address was. So I had to bother everybody in the network. Does that sound... Reminds me of a story. I'm trying to remember the story. Oh, yes! When I had to get Bob Smith's attention, what did I have to do? I had to interrupt everybody at 11:45 p.m. that night on that Sunday night. I had to disrupt everybody in the neighborhood just to get their attention. And I pissed off a lot of people, like a lot of devices on the network were pissed off by the broadcast. But you know what? I got Bob Smith's attention. But did Bob Smith shout back at me? No. What Bob Smith did was he discreetly walked over to me and said, it's 123 Main Street. So that's illustrated by the fact that the ARP reply is only going to be sent from the destination to the source and not in the form of a broadcast, because when the source broadcasts the ARP request, he's specifying his actual IP address and MAC address, so the destination doesn't need to go find it any other way. So let's just examine, before we talk about remote communication, what's going on behind the scenes over here. This is the logic that goes through the switch. And in our modified example right now, Fred over here wants to send traffic to Barney. They are connected through the same Ethernet switch that you're taking a look at over here. Every switch has a table and RAM, and there are many different names for this. Some people will call it the source address table. In the world of Cisco, it's known as the MAC address table. It's also known as CAM, Content Addressable Memory. Point is, when the switch boots up, it doesn't know anything. It doesn't know which devices are connected to which interfaces. But as soon as Fred sends that ARP request into the switch, now this happens to be a diagram that I took from a Cisco Press book. It's not correct fully, but if you take a look, that ARP request is going to actually go out of interface F03 and F04 in addition to F02, because switches take broadcasts and they flood them out of all ports except the port on which the message originated. It would be stupid to send the message back out of the port in which it came. So in this example, Fred needs to talk to Barney. Fred has Barney's IP address. Fred doesn't have Barney's MAC address. So Fred sends an ARP request. It goes into the switch. This guy, oh, well, Wilma will hear it. This lady will hear it. Betty will hear it. Barney will hear it. Guys, I need to have your cooperation, please. I can't continue if they're talking. So the message is going to go into the switch, and Wilma and Betty and Barney will all hear the ARP request, but most of them will disregard it. Who's the only person who will say, oh, yes, that's my MAC address? Well, if Fred specified Barney's IP address, Barney is going to be the only one that sends the actual ARP reply. So if you take a look at the table over here, the table doesn't know anything. But as soon as Fred's ARP request goes into the switch says, I know that this MAC address of Fred is now associated with the F01 interface, the Fast Ethernet 01 interface right over here. So when the return traffic from Barney goes back into the switch, this is how the ARP reply can truly be unicast. The switch doesn't need to send that ARP reply out of F03 and F04 because Fred's MAC address is already known to the switch. But when Barney sends his actual ARP reply into the switch says, aha, I know where Barney is and notes his MAC address and the interface on which that MAC address was heard, the switch now learns as traffic is sent into the switch. That's one of the reasons why it's called a source address table, because the switch learns about you when you're at the actual source of traffic, when you send traffic into the switch. So if you take a look over here, as the devices are sending traffic amongst themselves, the table will be fully populated, and that will create some sort of illusion of a virtual circuit existing between the ports, where the actual traffic does not need to leave any other ports except for the intended destination. Another diagram over here to show you that the source address tables on switches that are adjacent to each other, whether they're connected in a daisy chain or a hierarchical fashion, work the same way. But take a look at this. You got Fred and Barney connected to switch 1, and you got Wilma and Betty connected into switch 2 right over here. As far as switch 2 goes, when Fred and Barney send traffic into switch 2 through the gigabit 02 interface right over here, switch 2 thinks that Fred and Barney are directly connected to this actual interface. Fred's not, Barney's not, but their actual frames, the actual traffic goes into switch 2 at gig 02, which is why both Fred and Barney are associated with interface gig 02. And on the flip side, Wilma and Betty's traffic goes into switch 1 through gig 01, which is why gig 01 will actually bind the MAC addresses to that respective interface. So you can interconnect switches, it all works. You don't obviously have to be directly connected to a specific switch for the entry to be populated into the table. That's story number 1, local communication. Story number 2, remote communication. And now we got to get these devices called routers into the mix. And what happens is, let's change the numbering scheme up just a little bit. Let's say one of these hosts on the 1200 network, and by the way, the /8 is another way to write the subnet mask. It's called CIDR notation, CIDR, classless internet domain routing notation, which means it's much easier to say /8, and the 8 refers to the number of ones in the subnet mask, instead of saying 255.0.0.0. So /24, for example, would be the logical equivalent of 255.255.255.0. So that's what you're taking a look at here. Just like the switches have memory and tables, the routers have memories and tables. Switches connect nodes of the same network together. A node is anything with an IP address. Switches connect nodes of the same network together. Routers don't connect nodes together. Routers connect networks together. So think of the local streets as the switch ports. Think of the highways as the actual traversing through routers. So here, the source IP in this little example is going to be one of these machines over here. Let's call that 12001. The destination IP address, he got this from DNS, 14001, one of these devices right over here. I've abbreviated the MAC addresses for space. We're only going to use 2 hex characters. So now what happens is the source knows his IP address, he knows the destination IP address, he knows his MAC address, but once again we have the same problem. The problem is the source will never know what to put initially in that destination MAC address field. ARP replies will be cached, so successive requests will not require ARP, but we're just assuming there is no cache right now in play. So the source does the logical AND process, and he determines something different over here. He determines that the destination is on a different network, and he says, ooh, that's not so good. I can't deliver the traffic myself. The source realizes at this point he's got to get the traffic to his default gateway, the local router interface connected to his particular infrastructure right over here. So how does he do that? Well, he sends an ARP again, and this time the ARP is going to look something like this. Assuming his gateway's IP address is going to be, let's say, 120099. The ARP request will say, if your IP address is 120099, send me your MAC address. Notice that the source doesn't say if your IP address is 14001, because you can't talk to somebody directly unless you're on the same network. Routers never forward broadcasts. They have never done it, they don't do it, and they will never do it. Routers never forward broadcasts. If ARP requests are broadcasts, the furthest that this host can do is send a broadcast to his router and ask for some help. So all the other hosts in the switch will get that ARP request. So will the router interface right over here. This is the only entity that will send an ARP reply back, and the ARP reply will look something like this. My MAC address is BBB. So at this point, the source takes the traffic with these respective source and destination IP addresses, and now fills in BBB for the actual MAC address. The traffic gets up to this router interface right over here. The router looks at the destination MAC address and says, yep, that's me. And then the router says, wait a minute, that's not my destination IP address. So R2, router 2, consults his routing table, and he sees that he knows about this 14 network. If he didn't, he'd actually drop the packet on the spot. Router 2 happens to know about this 14 network, and his routing table says, to get there, you got to send the traffic to R1. So R2 says, I got to get the traffic to R1. Now, in reality, this is a simplified version of the routing table. It's not going to say R1. It's going to actually have the IP address of R1 that's directly connected to R2. So what's going to happen is, assuming that these are all Ethernet interfaces, the story is a little bit different on serial interfaces, R2 is going to send an ARP request. And there could be switches and PCs here. It doesn't have to be populated. It doesn't have to be unpopulated. It doesn't change the story at all. The ARP request will hit this interface and any other devices that are over here. And the ARP request will say, if your IP address is, so let's call this network over here between R1 and R2, if this is the 12 network and this is the 11 network right over here, let's call this the 9 network over here. If your IP address is 9.0.0.99, I need your MAC address. The ARP reply will come back from the left interface of R1 to the right interface of R2, and look what happens now. R2 changes the actual MAC addresses in the transmission. The new source MAC address is not going to be this interface. It's going to be this interface, the exit interface of R2. And the destination MAC address is going to be this interface right over here in R1. And R1 will say, oh yes, destination MAC address DDD, that's me. But wait a minute, that's not my IP address. So what's going to happen is R1 will say, do I know about that 14 network? And R1 does know about that 14 network. He knows he's got to get the traffic over here to R4. So once again, there's going to be a pair of ARP request and ARP reply messages that go between these two routers. R4 is going to give R1 its MAC address, and R1 will now send the traffic to the left interface of R4. We're almost home free right now, because R4 looks at the actual destination MAC address, says, that's mine, but wait a minute, that's still not the right IP address. R4 looks in his routing table and says, it's not me, but I'm actually directly connected to that network. So out of this interface of R4 will go an ARP request that says, if your IP address is 14.0.0.1, I need your MAC address. And once again, a new source and destination MAC address are added to that outer encapsulating layer known as a frame. And the traffic does reach this device. He finally says, yes, that's my MAC address, and yes, that's my IP address. That's the story of remote communication, and it's the same story as the candlestick story at the beginning of my talk, because I realized that from here to Rochester to Staten Island, quite a bit of distance. I'm not going to go and directly deliver those candlesticks. So what I did was I Googled for the nearest UPS store to where I live, and that turned out to be this UPS store right over here. When I brought the traffic to this UPS store didn't deliver the traffic to Staten Island, which I'm guessing is somewhere right over there. What happened was this UPS store found the next UPS store, or next UPS distribution center. And this UPS distribution center found the next UPS distribution center. And eventually, it got to my parents' house in Staten Island, New York, and everybody was happy. For remote communication, you'll notice there's a strict requirement to have two different types of addresses. The MAC address is changed with every hop, every network, every router that the traffic is passing through. And those are just like the UPS labels that are being slapped on and slapped off at each distribution center. They represent the distribution facility stop off, and that's how you actually can track your packages. That's how you can actually see where those packages are. But it wouldn't make sense if there wasn't a constant source IP address and a constant destination IP address. That's the function of the IP addresses here, the source and destination IP addresses, which never change throughout the duration of the packet's transmission. So when you think about it, we need to have both addresses because these addresses specify the next hop along the traversal of the traffic, but these represent the logical starting point and the logical ending point. And what happens is, every time a router says, yes, that's my IP, yes, that's my MAC address, no, that's not my IP address, what has to happen is the router's got to take off that MAC address information and put on some new MAC address information. IP addresses are found in structures known as packets. MAC addresses are found in structures known as frames. So what's really happening is the packet is decapsulated from the frame and re-encapsulated with every hop of the way, all the way to the actual final destination. So I got one more question now, because if we're being complete in terms of our network communication story in an hour or less, we got to talk about the fact that one IP address, by the way, am I still on right now? Sounds, can you still hear? Sounds a little different. One IP address could be the destination for multiple services. You could have one server that's running a DNS server, a DHCP server, one machine that can have a web server, an FTP server. So getting to the actual IP address is not everything and anything. We've got to find a way to actually get into that machine logically. I told you that the way in and out of a machine physically, with those actual ones and zeros represented with electrical pulses, is through the NIC, through the network interface card. Well, that doesn't help me out if the same machine is being used as a DNS server, a DHCP server, a web server, a file server, a remote authentication server, an FTP server, you name it, an SSH server. How do I differentiate between the various services that are running on the machine? Well, the mailman who brings the mail to this particular apartment puts the mail for Frank over here in box number 21, and puts the mail over here for Helen over here in box 80. Frank lives in apartment number 21. Helen lives in apartment 80. His full name is Frank Thomas Peterson, FTP. And her full name is Helen Teresa Thomasina Parker, HTTP, unencrypted web traffic, port 80 right over here. Same machine is used for an FTP server and a web server. So when the port number, and you can think of it as another form of addressing, when the port number is specified, that not only says which machine it's destined for with the IP address and the MAC address eventually, but it specifies which service on the machine the message is destined for. Ports come in three different categories. You've got the well-known ports, technically from 1 to 1023. And those are the ports that you would memorize for a certification exam, or the ones that I'll be drilling into your brain for network services and sysadmin and routing and switching. Those are the ports that are used by servers with the exception of one. There's one port that's used by a client, and that's a DHCP port 68 client port. Everything else is for servers. You got the registered ports, which is really a joke nowadays today. If a program comes out and the company wants you to use a specific service port, or whether some protocol that you're developing, you need some specific port, again, you got to register for that. Doesn't mean a thing today, because nowadays most traffic on the client's side will use one of these ports from 49,152 to 65,535. And the reason is clients open up ports on a dynamic basis. Servers have their ports opened up all the time. Ports are like open doors or open windows into a system. If a server closed a particular port, that's the essential equivalent of stopping the service. When the port is open, the service is accessible. When the port is closed, there's no service, there's no way into that logical portion, that logical software portion of the actual machine. A common misconception that bugs me is when people say firewalls close ports and firewalls open ports. Firewalls have never closed a single port in the history of the world. Firewalls have never opened a single port in the history of the world. Firewalls filter traffic, which means they look at the destination port or the source port and they say, yes, you can go through, or no, you can't go through, or yes, you can go in this direction, or no, you can't go in that direction. If you've got an SSH server, let's say, and on that machine port 22 comes up, the firewall has nothing to do with the actual port number that's open on the actual machine. So firewalls don't open or close ports. Don't let anybody tell you otherwise. Firewalls filter ports. So if you take a look, one final thing for today, where is this port number stuff found? Well, at layer 4 of the networking stack, whether you're dealing with one of the two common models, which have flaws, each of them, so I'm not going to even reference those models. There's another piece of traffic, and that piece of traffic is either going to be known as a TCP, Transmission Control Protocol segment, or a UDP, User Datagram Protocol datagram, which means the sending application will determine what type of structure actually holds the packet. Well, actually, technically, this will be encapsulated inside of the packet, but this layer 4 traffic will hold the upper layer data that's coming from above. And that's the only real thing that TCP segments and UDP datagrams have in common, the port numbers. So what are some common similarities and differences? The only similarity is really that both of the TCP segments and UDP datagrams have port numbers specified. That's how you get to the actual application. But the question is, what's the difference? And there are 3 basic differences. I got a bunch more, but I just want to focus on 3. TCP is connection-oriented. The source and destination have some taxiing, have some trailer action, have some before the message is transmitted communication to make sure that the message is transmitted. And because of that connection-oriented channel that's opened up between source and destination, every time you send a TCP segment containing data, the other side has to acknowledge it. Not a reply, just acknowledge it and say, I got the message. If the acknowledgement doesn't come back, the source will send it again. And it's for that very reason that we say TCP is just like death and taxes. People have told you there are only 2 things that are guaranteed in life, death and taxes. Well, there are actually 3. There's death, taxes, and TCP. TCP is guaranteed as death and taxes are. And of course, you cut a cable, you smash a machine with an axe, all bets are off. But provided there's a working connection between source and destination, TCP is right up there and guaranteed with death and taxes. Let me tell you about UDP. TCP is connection-oriented. UDP is connectionless. It's like you put a stamp on an envelope. You put it in a mailbox. If it gets there, it gets there. If it doesn't, it doesn't. You have no idea that it didn't get there. The person you write a letter to doesn't know that you actually sent him a letter. So UDP, not connectionless. There's no acknowledgments, of course. You don't have to say, I got your letter. And UDP, like everything in life, not death, taxes, and TCP, is definitely not guaranteed. So first question is, which one is better? Which one is better? Which one sounds better?
It depends on what service you're using.
Right, too good of an answer. Some people say TCP, some people say UDP, and my usual reply is, well, what are you going to wear when you're 90? And you actually answered that question already. Depends. It depends. TCP is where integrity is of great importance, which means file transfers, web traffic. And you're talking about email now, because change 1 bit in the message, it completely could corrupt the entire message. So TCP has a lot of additional overhead that we agree to just get the integrity, to just get it right. UDP is used for streaming and protocols like DNS and DHCP because it's quick, it's lightweight, the header is a fraction of the size of the TCP header, and it's super quick. And we say, look, we'll agree to have some potential data loss if you ask your server a question, your DNS server, your DHCP server a question, and you don't get an answer back. Well, you know what? Just ask the question again. Or for a stream, if you lose a bit or a byte or a bunch of bytes, you might notice a small degradation in the video quality or in the audio quality. But that's a fleeting moment in time. Voice over IP, if you're having a telephone conversation with somebody over the internet and you say hello, and they're using TCP, which of course never has happened in the history of the world, and their acknowledgement doesn't come back to you, your machine will actually send that hello message back again, and they're going to be getting duplicate messages. So for all those reasons, it makes sense where speed is of the essence to use UDP, and where integrity is of the essence to use TCP. So far, so good? What's your name, by the way?
Jess.
Jess? Don't go so far. Oh, sorry. So that's an example of UDP, where he doesn't know that I sent him those markers, and I don't know that he got the markers, and I just send it, and it was very quick. There was not a lot of overhead, but I got the message. Hopefully I got some of the message to him. If the messages didn't reach him, then you know what? I don't care. I'll just send it again. And that's why I would be firing markers all day long if I needed to, until I got a reply from him. That's UDP. I think I might have more. Hang on. I got to show you what TCP. Yeah, please, if you can. Uh-oh. Okay. Okay. All I need is 2. Let's do TCP now. Adriana, can I bother you for a second? Hi, Adriana. I'm Jonathan. Can I send you some markers? Say I got the blue marker.
I got the blue marker.
She got the blue marker. Yes.
I got the red marker.
She got the red marker. Yeah. She didn't tell me that she got the black marker. I have a copy of it in RAM, by the way. Not timer expired. Let me send her that same copy.
I got the black.
That's TCP. The additional overhead, the latency, all of that setup stuff, all to make sure that she gets the message and she gets the message as I originally intended it to be sent. That's why TCP is used for integrity. There's something known as the TCP three-way handshake, which is what Adriana and I just did, to set up the connection with UDP. I just fired off the markers. I didn't need to set up anything right over there. Follow me on Twitter, connect with me on LinkedIn, and come to my class. Thank you very much.
Got some markers for you.
Thank you.
No, not for now.